Good afternoon, and thank you for joining today's webinar from SPEC Innovations, What Comes After MBSE. My name is Elizabeth Steiner, and I'll be the moderator for today's webinar. First, I'd like to go over some quick housekeeping. During the presentation, feel free to send us questions, and we will get them answered in the question and answer part of the webinar. You can also interact with us on LinkedIn through our Innoslate users group or through Twitter using the handle @Innoslate. The webinar is being recorded and we will make it available to you after the live presentation. So be sure to keep an eye out for it in your inbox. Now I would like to introduce you to our presenter, Dr. Steve Dam. He'll be sharing with you the futuristic trend for the field of systems engineering and what improvements will help it grow. Dr. Dam is the president and founder of SPEC Innovations, as well as one of our DODAF training instructors. He has been involved with research experiments, operations analysis, software development, systems engineering, and training for more than 40 years. He has also received an expert systems engineering professional certification from Incosi. He currently is applying systems engineering techniques to various DoD, DOE, and commercial projects. Feel free to send Dr. Dam any questions through the LinkedIn user group or send him an email to steven.dam@specinnovations.com after the webinar. And now I'll hand over the controls to Dr. Dam and we will get started.
Thanks, Elizabeth. Appreciate it. So we're going to dive right into the current status of where we are. So model-based systems engineering. That's kind of been the thing now for quite a number of years in systems engineering. The definition from Incosi talks about a formalized application of modeling. That's an interesting thought, and we'll get back to that in a second. But you know, I just looked yesterday at the Google Trends on this term. And you know, that's the search term that people are looking for. And I tried a couple of different combinations of model-based systems engineering and MBSE and things like that. And they all showed up with this funny spike at the beginning, which I don't quite understand, in that the term wasn't defined by Incosi till 2007. So that's kind of an interesting factor. And then looking at the progression, it does look like about 2019, there's been a rise in that use of that term, and so you're starting to see that come in even more and more. So people are kind of, but one of the difficulties though is that definition that Incosi used really kind of fits any kind of diagramming framework. I mean, I used structured analysis back in the 80s. That would fit that definition. IDEF zeros, IDEFs, not just zero, there's like 15 IDEF models, and that's certainly that framework. UML, Unified Modeling Language, that certainly would fit that as well. So right now, a lot of people have equated it to SysML, and you know, that certainly is a diagramming framework that people are using. But you know, the problem is the benefits of MBSE and systems engineering in general have very often been a subject for discussion. And I know that because I actually worked on Incosi's value proposition initiative bit. And that was supposed to look at the what's the benefit of systems engineering, what's the benefit of model-based systems engineering, what's the benefit of Incosi. The group really focused on the benefit of Incosi more than the other two, but without the other two, if systems engineering and then model-based systems engineering doesn't have benefit, then why does anybody care? So we have to think about that, and we have to think about, well, what are we really doing? And are we modeling for modeling's sake? What are we getting out of this modeling? So a lot of it's, where did the data go? The key is that models kind of, people are very focused on not the data and the information you're trying to collect, which the models are a method for collecting information. But you know, you see that where they're often just kind of stuck still in kind of diagram mode. You know, and some people are still using tools like Visio or PowerPoint or even to do this modeling. So again, that means you have no really underlying database, you have no traceability, and of course, even if you use a database tool, oftentimes people don't capture all the metadata which you'd like to have, like even just a description of what does this box mean. I have a box and it says move process or something. And what does that mean? How does that fit? You need more of a description. They put these little cryptic names on the little boxes because that's what fits, and that way you can get as many boxes on the diagram as you can. But there's all kinds of other factors and things. Well, how long does that process step take, or what's the size of this information that's flowing down the pipes? What's the capacity and latency of the information that's passing over the pipes? So again, a lot of these things need to be captured and understood, and not seeing a lot of that, to be honest. It's fascinating to watch. And then, of course, what about all the relationships, the other things we're supposed to do in systems engineering? The principal job of systems engineers is to optimize the cost, schedule, and performance of the system, and to mitigate risk in each of those areas. So where's all that? Where's all that data? How's that being captured? Is that just lost, or is it not even being done? Again, so that's what I find curious. So again, I think we've gotten so wrapped up in the modeling part of MBSE, we've kind of forgotten about the data. And both the Office Secretary of Defense for Department of Defense's Office Secretary of Defense and the SERC, which is the Systems Engineering Resource Center, which is a UARC that is associated with DoD, both have some solutions on how to move forward. And they've pushed forward this initiative called Systems Engineering Modernization. And so they've recognized that there are different systems engineering practices that require integration. And here's the picture from it. This is one of their slides here on the right. And you see in there, the center is SE, and of course by that they mean MBSE. And then so they have these other things around it that they say are different somehow from systems engineering. And of course, Agile really usually means Agile software development. There's some discussion, there's an Agile systems engineering development approach too that's different, by the way, very different. So those kinds of things there. So again, this is kind of a little cryptic as to what they're trying to do, but they particularly wanted to focus right now on 4 areas: digital engineering, MOSA, which is Modular Open Systems Architecture approach. I keep forgetting. It used to be called architecture. It's the approach, and then of course, usually that approach is associated with an architecture. Anyway, mission engineering and agile development. So all these different terms and things have been coming into play, and they see them as separate practices. I'm not sure I've looked at it that way personally, but let's go on. And so the guys who are helping develop this, response to it, to SE modernization, in fact, are the SERC. Again, that's that UARC. And so it's a research center that the DoD has helped put together. And the key is, if you look at the emphasis of digital engineering transformation using a layered model with data storage and transformation at its core. So you can see this picture, and this sometimes is called the bomb cyclone diagram, by the way, which is kind of funny. But if you look at it, the center of it clearly is data. It's all about the data, and that's what we need. We need a more data-driven approach to systems engineering. And so we want to come up with, what is that? What does that look like? Because that's going to be the future. If they're serious about where this is going to go with SE modernization, and they really want to push forward, they're going to have to start focusing on the data. So we're beginning to coin the term data-driven systems engineering. This is actually in use by other people, but I haven't seen a really good definition of it. And so there's a process going on right now that the group for doing the lifecycle modeling organization is beginning to look at this definition and see if that's something they want to sign up to. But anyway, so looking at this approach, if we need something really as a common language. So we need something that helps us integrate these things. It's not a matter of that they really are fundamentally different practices. They're all part of systems engineering. So we need that common language to help bring them together. And so a language approach, you could really focus on the data and less on the form, which is what the model really is. A model is a way to graphically depict information, which is great, and certainly that helps communicate. But there's so much information you're trying to capture and work with, and not all of it's easily viewable in a pretty little diagram of some kind. Certainly the 9 diagrams of SysML can't handle all the information that's needed. So we need to go beyond that. And so that the idea is called this data-driven systems engineering approach. And here's the definition that we came up with that we think is pretty good. It's the transformation of user needs to requirements for design engineering, okay, and the transformation of design engineering data into verified and validated systems level information for decision makers to make better decisions throughout the life cycle. So it's a very simple definition. It's very clear. I think any systems engineer will look at that and say, yep, that's my job. I'm supposed to give the design engineering guys the requirements they need to help go off and build or buy what has to happen. And then I'm going to take their results and bring it up to the systems level as part of the V&V process, and then make it available to my decision makers. Excuse me. So if you think about it, that having those stakeholders in this definition helps us answer that first question we talked about, which is why, what's the benefit of systems engineering, right? And that's what we want to show, is that we have stakeholders who we're helping benefit so that design engineers get those clear, easy to understand requirements, and the decision makers get the information they need to make good decisions. And so hopefully that is something that people can resonate to. And now the value of systems engineering isn't even in question. We know exactly what we're doing. We know exactly why we're doing it. And so people can see the value. So fortunately, there is a language that already supports this, and it's called Lifecycle Modeling Language. And I know if you've heard some of our webinars that we push LML a lot, because we found that it is something that works, and it is something that's an open standard. So again, if you're not familiar with Lifecycle Modeling Language, it was developed by a group of systems engineers, much like many of these other languages are. And so, the group of us realized that SysML just wasn't meeting the needs of the systems engineering and program management communities, and particularly it wasn't speaking in a language that was easily understandable by those groups. It was a very much software-focused language, which isn't a surprise given that SysML is a profile on Unified Modeling Language, which is a software engineering language. Again, LML is managed by a not-for-profit organization called Lifecycle Modeling Organization. The steering committee has been always, in fact, led by Dr. Warren Vanneman. Dr. Vanneman is a retired Navy captain, and he's also a professor of practice at the Naval Postgraduate School. So you can see it. This obviously is not a proprietary standard in any way, shape, or form. When you've got a government person actually leading it. LML is taught all around the world, and you can see it partially because it's available through the Innoslate tool, and available, and people are using it to help do in the educational community. And that part of that is because LML is really easy to learn and use. And of course, you can extend it to make it better, to make it fit some of the things you need to do. You can see the learning curve is obviously a lot less because that little thin paperback gives you the essential of what you need for LML, whereas to really understand the 9 diagrams of SysML, you need those 2 books that are stacked next to it. So it's pretty clear that LML is a lot easier to learn. Anyway, so if, by the way, if you have learned SysML, you will find jumping into LML is very easy, much easier. In fact, hopefully it'll be a relief to you. Anyway, so again, LML has proven very strong ontology. It's been out since 2013, so it's been almost a decade out and available. And been used and applied in a variety of different ways and by a variety of different people. So I think people are resonating to it, and we're seeing that more. And we think that can form the basis for this data-driven systems engineering. And again, if you're not familiar with LML, it is set up, it's a little more than an ontology, actually. It's a real language. So if you think of the classes represent our nouns of our language, the relationships between the classes are the verbs of the language. Well, this also defines attributes on the classes, which those are adjectives, and attributes on the relationships. Those are adverbs. And so you think about that those language elements are actually stronger than an ontology, because the ontology, usually if you go to a tool like OWL and things like that, they don't have the concept of attributes on relationships. And that actually simplifies the language a lot, as it turns out, and makes it much less cumbersome to do some of the things you need to do. So I think you'll find that helpful. And a lot of people say, well, isn't this too simplistic? Well, yeah, there are these classes. There's roughly 20 defined classes. There's classes and subclasses. If you include both together, it's roughly 20. There's 12 primary classes, and there's, when you add in the other ones that have been defined, it's 20. So that's still a lot of stuff that you get connecting to each other. And as you see the relationships, everything's related to everything. So traceability is very easy to implement because you have that connection between the information. So it's easy to put the stuff in the bins. And then of course, if you want a subclass and add to that as you need to, and we've certainly done that many times, as we've needed to for particular programs, you can do that. It's easy to explain the delta that way. People can understand that base language, and then, oh, here's the little bit extra that we added to that. Okay, great. That's easy to represent and easy to work with. Also defined 3 diagram types as mandatory, because we thought the action diagram provides that behavioral modeling that we need. The equivalent of that in SysML is the activity diagram. The asset diagram is a very simple boxes and lines kind of diagram where you put pictures in, things like that. But basically, it's meant to be the physical side of it. And so that would be very close to an IBD in SysML. And then there's a third diagram that I don't believe is in SysML anywhere, which is the traceability diagram, the spider diagram. So this shows me all my different entities that I've defined in the different classes, and then their relationships between them. So I don't know of an equivalent in SysML for that. Okay, so how do we implement DDSE? Okay, so again, we think we need to cover all the aspects of systems engineering in this data-driven approach. So we need tools that can support the activity. You're not going to do this by hand. We've given up that long time ago. I mean, I gave it up 30 years ago, so there's no need to reinvent that wheel. So the key, and that's because there's a massive amount of data you've got to curate, you've got to work with. So you need to use database technologies. We've had database technologies forever. so there's just, that's not something new, and let's not reinvent that wheel either. So okay, so we're going to use the database technologies that are out there available for this. And the key is that you need tools that can include all the different aspects of systems engineering, right? Requirements analysis management. I need to do functional and object analysis. I'm still going to do object analysis. I'm not ignoring objects, because that's fine. That's a great way to visualize things in certain implementations. Modeling and simulation are of course critical. We need to do verification validation, of course, risk analysis, cost analysis, schedule analysis. That's kind of the minimum. All right, there's lots of other kinds of analysis we use in systems engineering do trade-offs and other things we have to do. But as a minimum, I need that, okay? And then the tools need to support a modern computer architecture. Okay, today that's cloud computing. I'm sorry, people are still using desktops. I feel your pain, and particularly when you have to install the latest version and things aren't compatible and messes things up. When the operating system changes and it locks down other stuff that causes problems. Anyway, so that's a much more effective way. And of course, those people are worried about cloud computing. There are plenty of secure clouds out there now today. Okay, at all levels of security. Okay, I've seen them at every level. The Department of Defense provides, Department of Energy, NASA, they've got it. So that's not a problem. And of course, the key is you also want tools that have an open architecture, because you want something that's easy to move the data between the tools. Okay, you cannot expect the world to adopt just one tool. It's just ridiculous. That's not going to happen. And so, in fact, I wouldn't even advocate that. If you actually had just one tool out there that said it could do absolutely everything, that'd be silly. Now, that may be able to do everything in a certain area, but not everything we need to do. Okay, so we'll recognize that. So we're going to look at today's tools. What's the current status of today's tools? So many of the tools today, in fact, I'd say most of them are based on 20th century technology. They were designed in the 1990s. They've evolved since then, but most of them have not been re-architected to take advantage of new technologies. So they're still kind of old tools, and they kind of feel it. They look at, you can see it. And so that makes them kind of difficult to use by compared to modern standards, what we're used to in terms of user interfaces and things like that. Particularly installation kind of problems. You always end up with desktop software. Just had an instance where someone was struggling with MATLAB because suddenly it stopped working because they had a system update. Those kinds of things are problems with the desktop tools. Anyway, another is that the models do not execute. So very often, most of the tools are designed without a simulation backbone underneath it, and particularly Monte Carlo. Those who don't use Monte Carlo probably don't realize how important it is. We, particularly early in the life cycle, have a very little understanding of the exact value of anything. So you need to be working with distributions and things like that give you across that spectrum of analysis, and so that Monte Carlo becomes really critical. And of course, not having them executable is a big problem. Particularly your behavioral model, because that's how you really want to see the information and have it connected. And you also want it constrained by physical environments. So they're physical models. So you've got that to work. Also, there's limited lifecycle management. Very often you will, most of the people are, again, if you're doing modeling, MBSE, most people are focusing on this modeling drawing kind of tool, not looking at the whole set of things. So you need a lot more tools to pull that together. In fact, what you find people are doing is kludging together 6 or 7 different tools to do what they're trying to do. And again, they're not redesigned to interoperate, so they don't do that well. And again, of course, that lack of collaboration. If you're really working in what's primarily a check-in, check-out desktop kind of environment, even the ones that say they're a cloud system, what they mean is that you go to the cloud and you download the database and so you check it out, check it in. That's not collaboration. That's not what we mean by collaboration. So that's not where you get there. So that's kind of where most of the tools are today. So the question is there a set of tools that can meet the need? Well, actually there is, and Innoslate's one of those tools that start that process. So simplicity, again, it uses LML, implements that. It's a cloud-based tool, cloud-native tool, so it uses web browser interface. So there's no downloads for the client side. Also auto-generates all the diagrams and dashboards and things like that from the data. So you are getting views of the data, and when you make a change in a data element, it automatically updates it in all the other views. And of course, that's what you want, right? You shouldn't have two different views of the same information set and have different information in it, right? that's bad. Collaboration, of course, again, the cloud helps us with that, so we can have real-time chat, real-time indicators for who's working on what when, things like that. So you can work with that, no check-in, check-out. Again, it also has proven to be able to be used for model-based, or we're starting to call them data-based reviews. So DBRs rather than MBRs. So that's been proven over the years to do that with it. Also accuracy, we have full discrete event and Monte Carlo simulators. They do look at cost, schedule, and performance factors as you're doing the model. They can be physically constrained as well, and geospatially constrained, even with addition to with another tool we're going to talk about in a minute. So again, there's also it's using NLP heavily, that branch of artificial intelligence for requirements quality and traceability. There's also an intelligence view, which is NLP driven, that 68 heuristics that look how good your model is. So there's a lot of analytics built in to Innoslate. There's also scalability. So again, the cloud helps us a lot with that problem. And of course, you have to design the software to scale too. It's not just having the hardware side of it scale. If the software isn't built and designed to scale, then yeah, you have real problems. And so we've tested 10 million entities and 1,000 simultaneous users. We know that's not enough, and we're continuing to push that envelope right now. And then full lifecycle management, it does support everything in systems engineering, from requirements analysis management, modeling simulation, test center, so all those capabilities. But probably one of the most useful things and most easy entry points is the documents view. What that allows you to do is set up all your documentation, and then you can use all those diagrams and things you build within the tool and can be put right into that live digital artifact. And so now I've got the digital artifact I can work with, and I can reference, and I can use the model-based reviews with. And then if I need to output it to paper, I would just output it to Microsoft Word, and you clean it up a little bit, and boom, you publish it, and then that becomes your shelfware. And so again, I can archive that as an artifact in the database, and so I can track that as well. Of course, then we got the interoperability capabilities. So we've been working really hard on that because we have an open architecture. We actually do subscribe to the whole concept of modular open systems approach. And so we have open APIs for that, so that makes it a lot easier to do things. We've built round trips using RecIf and Excel as well. So we can do some back and forth, although we tend to see more importing of information into the tool. Integrations with Systems Toolkit, MATLAB, GitHub. Again, I'll talk about that more in a minute. And again, the APIs are open and available. So another tool in our toolbox is Supatra. So Supatra is built on Innoslate, and it's designed for standard operating procedure analysis and development. And so it has some specific things, improved in extras, I should say, in the functional model. But one of the things we've been working with is taking actual natural language text SOPs, because that's how most of them are written today. And in fact, most people just go word process and create these SOPs, right? We can ingest that and actually automatically create, using NLP, the behavioral diagram. And then that behavioral diagram is then what's simulated using a special extension of the Monte Carlo simulator to show when your SOP is not going to meet the available operational time window. In other words, the time before things go bad. So again, some very nice features with this, and this is continuing to evolve. And last but not least, definitely is Ansys. So the Ansys tool suite is basically the gold standard of design engineering tools. they have just about everything. And what they haven't bought, what they didn't have, they bought recently. All right, they picked up AGI, who was the systems toolkit guys. So so they now own STK. They also picked up Phoenix Integration, so they have Model Center. So now this helps you with some of that interaction between tools and be able to move data back and forth. But you can see by the little slide on the bottom part of the slide here to the right, all the different things they do, all the different disciplines that they support. So what we found so far that, sometimes you do want to move data back and forth directly, but sometimes all you really want is the output from those, the results. And so much like our CAD viewer that we use, and we can use their CAD tool, SpaceClaim, and we've done this where we've taken SpaceClaim data and show it as a CAD drawing. But it's more to curate that design information and design engineering information and abstract it up at the systems level, so you can, again, so I can go make those decisions, so I can support V&V activities with it as well. So again, Innoslate gives us this documents view, the requirements view is part of that documents view, which brings in the quality checker for requirements, modeling with 26 diagram types and 5 chart types, and we're going to keep doing them because there isn't enough diagram types actually to show it visually. So that you can't actually come up with enough modeling types to actually show all the data we're looking at. And then design engineering integrations has been a major thrust for the last few years. Simulation, I manage both discrete and Monte Carlo, and of course our test center. And of course, don't forget about risk. So we have risk matrix, risk burn down charts. We've got timeline diagrams, Kanban boards, Gantt charts, almost any way you want to visualize time. And then cost. So again, be able to work breakdown structures or cost breakdown structures, and also then integrating those together with the simulation and making sure that it all links together. So you can do both a static roll up of the cost, or you can do a dynamic roll up through the simulator. And of course, Sapatra. So Sapatra is covering that last part of the life cycle, which is the operations and support cycle, and making sure that that part of it is done well. And of course, that starts in the design phase, but it's heavily used and updated during the operations phase. So for a digital ecosystem, we're recommending Innoslate's digital ecosystem, and somehow something happened here. Okay, and that's basically Innoslate's kind of the core of it. We've got CAD here as well. We've got GitHub, which is our software engineering tool repository. We have, since STK and MATLAB are both desktop applications, we have to go through a Java web app to make that connection. So the individual desktop apps are sitting on your desktop, and then they can interact with the cloud using this Java web application. Again, right now, most of the Ansys tool sets, we're doing more of a SneakerNet kind of link to it. We're looking at how to automate more of that, but again, that becomes contextual, and so we're working with Ansys as a partner there. We've looked into LabVIEW. We'd like to build that interface more completely, just that's not quite gotten there yet. We have a prototype for the Selenium that we're hoping to get into version 4.7, which is under development right now, but that may have to be a later version. And then we are native already with the HoloLens. Turns out that the HoloLens uses the browser interface that we have, and so now you can go in and use this augmented reality capability with Innoslate today. So that's available now, easy. So again, we have a lot of ways to use the modern technologies and apply them to what we're trying to do. And so also MOSA architecture. So again, as mentioned, we are structured that way. So we got these APIs that connect. Our user interface is written in JavaScript. There's a Java core for Innoslate, and then that helps organize all the tables in the SQL database. And so the nice thing for everybody is that, guess what? You're not in data lock. Okay, vendor lock equals data lock, which means the problem with vendor lock is that I can't get to my data if I need to, except through their tool. You can go directly to the SQL database if you need to. So you're never in that lock point. So we think our value is provided in the way we use the Java core to organize the tables and think information that's in there, and then the user interface to help you do your analysis and activities that way. So we've focused on giving you access to your information. And so in fact, if you decide that, gee, our plugin, our user interface isn't sufficient, you want to build your own, you can. People are doing it, and it's not that hard. Okay, so how does LML, DDSE, and Innoslate Ansys tool suite support the systems engineering modernization? Well, so I want to go circle back to that because I think it's important. So digital engineering, well, again, the suite of tools we have cover the full range of tools you need to create a digital twin. I mean, Ansys tools by itself at the design engineering level got it covered. Okay, I'll just tell you. And then we're covering it at the systems and program level, and so that all the way up to the mission level too, as you'll see in a second. MOSA, of course, functional analysis actually is one of the things that helps you build a modular open systems approach, because the functional analysis allows you to allocate functions in many different ways. So since Innoslate provides complete functional and object analysis, again, we have all the 9 SysML diagrams. So we have a number of the other UML diagrams, class diagram, things like that. So those are just views of the information to us. We don't care what kind of analysis you want to use. You can use any type you want. So again, that's available for you. And of course, LML and Innoslate has some unique interface diagrams to help you do a better job of looking at your interfaces and understanding them better. And then also, our own MOSA architecture enables modular use of the data. So I think we've subscribed pretty well to MOSA here. Mission engineering, we already could do a lot of mission analysis work using just Innoslate's simulators. But when we added the SDK capability, that really gave us the full mission engineering capability, because the functional model has to be constrained by the geospatial environment, and that's a key part of mission engineering and what you're trying to do. So again, that gives us that whole ability to plan, organize. You, of course, can build ConOps in Innoslate. We've always been able to do that, things like that. So again, the kinds of things you do for mission engineering, we've got it covered. And last but not least is Agile. So again, we do Agile software development. We've done Agile software development since 2010 with Innoslate. And so we understand that problem and how to integrate between the system side and the software side. And so we provide that direct capability using GitHub and Selenium in the future, near future. And of course, we got Kanban boards and other Agile tools to help you do an easier job with your Agile development. We also have worked on the alignment between sprints and epics with the standard systems engineering technical review events. Again, and particularly if we do data-driven reviews, we can speed up those setter events significantly. So and do a better alignment with the software speed that they're working at. So in summary, systems engineering modernization requires us to, I think, requires us to use 21st century technologies to design and build the future. And so we need these technologies to break down the walls that have been erected between these modern practices. And so we believe that LML and the Innoslate Ansys digital engineering tool suite will really help us break down those walls and create that digital ecosystems that you need. So again, it's really all about doing systems engineering well. That's what we're here for. That's what we're trying to support. So Liz, I think I've got some time for questions. I went fast enough.
We haven't received any questions yet. So first I want to tell everyone how to ask questions. On the right, you'll see a panel that says questions. Go ahead and ask your questions there, and don't worry, you'll be anonymous. But in the meantime, I'd like to announce our next webinar. It's Innoslate tips and tricks. So Dr. Dam is going to be giving you this full overview of the tool, and he's also going to be giving you his expertise on how to best use Innoslate. And this is a great webinar for beginners or even advanced users to really get to know the tool better and use it more efficiently. And that will be November 15th at 11 a.m. Eastern. And if you can't join us live, be sure to still register to receive the slides and recording. So we'll give everyone another second here to ask questions, and if not, we'll go ahead and wrap up the webinar.
Okay.
And of course, we have lots of resources that you can join us for. There's training, specinnovations.com for training. We do custom workshops, and we'll work with you. There's lots of books as well. You can actually download our Real MBSE book and our DODAF book right from the website. There's lots of other educational videos. Feel free to join us on LinkedIn and all our other, we have Facebook as well. We have one question. How does the CAD interface work with Innoslate?
The chat interface?
The CAD interface.
Oh, the CAD. Okay. Yeah, so the CAD interface, you upload a file. That's one of the file types of CAD. And so then the viewer sees it. And so I can actually probably show it. Maybe that's the best thing to do. You do that real quickly here. Artifact. And let's look for CAD models. This is probably, this is probably one of the prettiest ones. There we go. So let me open the entity view here. I could double click it, I keep forgetting to, and view CAD. So this takes a second to get it started up. So this is actually a zip file, and you can see the different aspects of it here, and you can rotate it, see all the different things that are available in it. So this zip file, it contains the .obj and a .mtl file together, zipped. And so that gives us this nice, very pretty picture. Did that answer the question?
I think that did, but let us know in the questions. Our next question is, can JWA support Python or C++ codes beyond the existing SDK and MATLAB?
We've not done anything with that yet, but that's something certainly we could look into in the future. And I'd certainly love to explore those options and see what we can do.
MOSA is a new term to me. What is the origin and how is it applied?
Yeah, I hear the MOSA term really came into being, well, open systems architecture and modular architectures have always been discussed separately. The first time I heard MOSA was probably Department of Defense, and that's, I believe, where most of that's coming from, and they're the ones driving it. I believe they've gotten to the point now, though, that they actually have managed to get it into legislation. And so some of that's actually law now that we're supposed to go off and do these things. Don't know how you legislate that, but okay. I guess they can legislate anything.
Other than just linking a CAD drawing or model, can the data be used in Innoslate?
Yes, so you can export other files like the BOM, the bill of materials files, things like that, and upload those and bring that in separately as a separate file. The just.obj lets you actually expand it into its different elements, and it will create entities in Innoslate that you can then use to trace back requirements and things like that. So we're working on ways to see if we can't do more. Can we push the requirements to the tools, to a CAD tool or to any other tool, and then have it associated, whatever the design work was done associated with, so you get the immediate link back to the requirement. And so that is something we're working on that we don't quite have done yet, but it is in the roadmap.
Thank you, Dr. Dam. That's all the questions that we've received today. If you have any other questions, feel free to reach out to us after the webinar. We'd like to thank you again for joining us. As a reminder, we will be following up with you very soon to send you a link to the recording and the presentation slide deck. We also encourage you to visit our website and our blog, as well as connect with us on social media. That concludes today's presentation. We hope to see you at our next webinar. Please enjoy the rest of your day.